In this online lecture, I'm going to introduce alkanes and how to name them using nomenclature. So let's start with the most simple alkane right here. An alkane, by definition, is a molecule that has only carbon and hydrogen, and all the carbons are sp3 hybridized, which means all the carbons have 4 single sigma bonds around them. This is one way to represent an alkane, and this is called the keykule structure, or sometimes we call it the expanded version of the molecule. Another way to represent this alkane would be this way, the condensed way. Notice simply we're collapsing the hydrogen bonds down and representing the molecule as CH4. Now, because carbon could make 4 bonds, you could have longer chain alkanes like this. This molecule is 3 carbons long. This would be his expanded version. His condensed version would look like this. We would call this a straight chain alkane. Now here's another consequence of carbon's ability to make 4 bonds. Look at this hydrogen right here. Instead of having a hydrogen, we can actually connect another carbon. And that particular carbon would have to have 4 bonds, so we can put 3 other hydrogens around him. This would be called a branching alkane. We simply think of that carbon as acting as a branch on the 3 carbon long chain below. We could also represent branching alkanes in their condensed form like this. This brings us to another vocab term we should know. Let's compare this molecule right here to this molecule below. If you count the atoms here, you'll notice that both these molecules have a total number of 4 carbons. And also, if you count up the number of hydrogens in each molecule, you'll see that both these molecules have a total number of 10 hydrogens. These molecules are called constitutional isomers. And let's look at the characteristics of constitutional isomers. These molecules have the same number of atoms, but they have different connections. Again, our example here, we have the same number of atoms, but the connections are different. The top molecule has a branch point on the second carbon, and the bottom molecule has no branches at all. It's just a straight chain alkane. Now, let's talk about how to name alkanes. Let's say we want to name this molecule right here. To do this, you follow a series of steps, and make sure you follow the steps in the order that I'm about to show you. If you do so, it makes this process very simple. So, here's step 1. Let me show you this. The first thing you do is find the longest chain of carbons. Notice if we start right here, let's say 1 carbon here, this would be 2, 3, 4, 5, 6, 7, 8. That would be the longest straight chain of carbons. And what we're going to want to do in step 1 is box that longest chain. In fact, on your orgo exam, that's exactly what I'd like you to do on the test. The longest chain gives us what's called the parent name of this molecule, and since it has 8 carbons, the parent name would be octane. The ANE ending is reminding us that this molecule is an alkane, and the OCT part comes from the number of carbons. In fact, we should memorize this chart right here. 1 means meth, 2 means eth, 3 means prop, 4 means bute, 5 pent, 6 hex, 7 hep, 8 oct, 9 non, and 10 dec. So, going back to our example here, that's the parent name of the molecule. Now we're ready for step 2. In step 2, we have to correctly assign numbers to the carbons in the longest chain, in the box. For instance, let's say we started numbering from right to left. This would be carbon 1, 2, 3, 4, 5. But let's pause right here for a second. Notice on carbon 5 we have a branch point, which means numbering from right to left would give us our first branch point at carbon 5. But let's see what happens if we number it from left to right. If I start here, this is carbon 1, 2. Let's pause at carbon 2 here because notice numbering from left to right gives us our first branch point on carbon 2. This means that the correct way to number this chain is from left to right because we always want carbon 1 to be closer to the first branch point. So let's continue assigning our numbers here for the rest of the carbons in this box. Now we're ready for step 3. What we want to do here is circle all the branches, or in other words, the substituents in this case, and label them. For instance, this is a branch or substituent right here. He is 2 carbons big, and remember, according to our chart, 2 carbons long is eth. But since he's a substituent, he's not the main show, let's say. Instead of ethane, we change the ending to YL. So we'll call him a ethyl substituent. Let's use the same reasoning for the other substituents here. This one right here is 1 carbon big, which means meth. And since he's a substituent, we change the ANE ending to YL. That means this substituent over here is the same thing. He's also a methyl. Now we're ready for the last step, step 4. Here we list our substituents in the name of the molecule, and we label them according to which carbon they're connected to on the main chain of this molecule. For instance, the ethyl substituent happens to be connected to carbon 4 within the chain. And what we do is list our substituents in alphabetical order in the name. And since E, ethyl, comes before M, methyl, we're going to list him first. And this is how we do that. We simply say 4-ethyl. We need to do this for the remaining substituents. Notice we have a methyl on carbon 2 and a methyl on carbon 3. So here's how we place this into the name. We would say then -2, 3, and since there's 2 methyls, we would say di for 2, methyl. So the name of this molecule is 4-ethyl 2,3-dimethyl octane. Think of the advantage here. Knowing the name of this molecule can help you generate the structure. So we would read this as octane, an 8 long carbon chain that has an ethyl on carbon 4 of the chain and 2 methyls on the chain, one located at carbon 2 and another located at carbon 3. So the name is basically a description of the molecule. Now, in order to get this down, you need to see many examples, and you need to handle certain situations that you might find yourself in. And what I'm going to do here through the remaining examples is show you what situations you might encounter and what to do about them. So let's look at the first sample problem here. Name the following molecule. Well, of course, let's do step 1. Let's find the longest chain. It looks like that this might be our longest chain right here. Notice it has 1 carbon here, we have 2 right here, then 3, then 4, and then 5. However, let's see if we could find a longer carbon chain. What if we called this our longest carbon chain? Notice if you count, you're going to get 1 here, 2, 3, 4, and then 5. So notice this box is also 5 carbons long. And technically, that's not the only way. You could find the longest chain going this direction. This box is also 5 carbons long. So what do we do in this case? What do we pick as our longest chain? Well, what we're going to see here in nomenclature, the beauty of this system is that it doesn't matter. You can pick any one of the chains, and we're still going to end up with the same name. Let's call this our longest carbon chain and name the molecule, and I'll prove to you that if we used a different chain, that we'll end up still getting the same name. So here we go. Remember, the longest chain of carbons in that box is 5. 5 means pent, so the parent name of this molecule is pentane. Now let's go to step 2 here. Let's correctly assign the numbers. If we number from left to right, we're going to get 1, 2, and right away on carbon 2 we have branch points. If we number from right to left, then we'd get 1, 2 here. Notice in both situations we end up with 2 branch points on carbon 2. So it doesn't matter which direction you pick here, any one will lead to the same answer. But let's stick to left to right numbering here. So that means this would be carbon 3, 4, and 5. Now we're ready for step 3. Let's circle and label our substituents. Notice we got this thing right here, which is of course a methyl. We got another one right here. We got one here as well, and another one right here. Remember, the substituents are the things that don't make it into the main chain. We're now ready for step 4. Notice where all of our substituents are. We have 2 connected to carbon 2 and another 2 connected to carbon 4. What we need to understand in this example is that every substituent has its own number, which means in the name you'd have to list this as 2, 2, 4, 4. So notice each number calls out each substituent. 2 methyls on carbon 2, 2 methyls on carbon 4. And since there's 4 methyls, we would say tetra, meaning 4, methyl. So the name of this molecule is 2244 tetramethylpentane. Now again, take a few seconds and try to imagine if, given the name, could you think of this structure? Pentane would remind you that it's 5 carbons long, tetramethyl would remind you that there's 4 methyls, and the 2244 are telling you where to place those methyls on the longest chain within the molecule. Now, let me show you that if you use a different chain, you would still end up with this name. Let's go back to the beginning here, and let's just choose this long chain right here. If you number the carbons, you should be numbering from left to right, or it doesn't matter, from right to left for this particular case. And notice right off the bat here, the parent name would still be pentane. Let's look at our substituents here. Notice you have still 4 methyls, just like we had before. And notice where these methyls are connected to the main chain. You have 2 of them connected to carbon 2, and you have another 2 directly connected to carbon 4. So again, you would say parent name is pentane. You have 4 substituents, 2, 2, 4, 4. They happen to be methyls, so we would say tetramethyl. So notice we do get the same name after all. But this is why we go in steps 1 through 4. If you don't name molecules in this order, you might end up erroneously with a different name for this molecule. And some of the most basic questions on an Orgo 1 exam are nomenclature questions. It's almost a sure thing that your professor is going to ask you to name a molecule. But we're going to see later on that we use nomenclature constantly throughout organic chemistry. So this ends up being just a basic skill that we'll use for the rest of our Orgo career. Now, there's another aspect of nomenclature that I want to discuss here. We're going to see that some molecules are named using the system that we just used here, and that system happens to be called the IUPAC system. But other times, the molecules are going to be named by their common name. Let me show you what I mean by that. Let's name this molecule using the steps. This right here, of course, would be the longest chain, making the parent name of this molecule propane. He's 3 carbons long. Numbering the carbons here wouldn't matter. In this case, left to right is fine. Then we'd want to label our substituents here. We only have 1, the methyl, and he happens to be on carbon 2 of the long chain, so his name happens to be 2-methylpropane. And this is what I mean by his IUPAC name. However, this molecule has a common name. They sometimes refer to it as isobutane. These common names were developed before the IUPAC system came around. And it really depends on your particular Orgo professor on whether or not you need to know common names. Most, if not all, professors will have you definitely know the IUPAC name, but some of the more old school professors might want you to know common. It's best that you ask your professor just to make sure. So let me show you some other examples of this. Let's first get the IUPAC name of this molecule. Notice he's 4 carbons long and he has a methyl on carbon 2. So his name would be 2-methylbutane. His common name happens to be isopentane. This molecule right here, if we were to name him, notice he's 5 carbons long and he has a methyl on carbon 2. That would make him, his IUPAC name, 2-methylpentane. His common name is isohexane. And another example here, just to be safe, is this molecule right here. He happens to be 6 carbons long with a methyl on carbon 2. That would make his IUPAC name 2-methylhexane, making his common name isohexane. Now, let's get back to our IUPAC nomenclature here. Remember, I want to show you different situations that you might find yourself in and what to do about them. Let's name this molecule. Let's start here with step 1. Finding the longest chain, we would see that this is the longest chain of this molecule. That's 6 carbons in the box, making this parent name hexane. Let's now go to step 2. Should we number left to right or right to left? Well, numbering left to right, we have 1, 2, we get to our first branch point right here. But if you number right to left, you also get a branch point on carbon 2. So the question is, what is the correct numbering system? But notice when you number from left to right, you end up with 2 branch points on carbon 2. And if you number from right to left, you only have 1 branch point. And what we're learning here for this example is what to do in this case. We simply number in the direction that has the greater branch points. So therefore, numbering left to right would be the correct way, not right to left. So let's fill in the rest of these numbers here. There's the 1, 2, 3, 4, 5, 6. We're now ready to proceed to step 3. We already have our substituents circled here, so let's just label them. Notice they're all methyls. Which means we're ready for step 4 to complete him. Let's put this all into the name. There happens to be 3 substituents, so it would be 2, 2, 5, dash, tri, because there's 3 methyls. So the name of this molecule is 2,2,5-trimethylhexane. Now, let me show you another problem, and we're going to see how nomenclature can help us answer this. For instance, this problem says, are the following compounds identical or constitutional isomers? Well, at first glance, they definitely don't look exactly the same. But remember our definition of constitutional isomers. These are molecules that have the same number of atoms, but they have different connections. To better understand these molecules, what you might want to do is try to attempt to name them and see what you get. If these molecules have the same number of atoms, but they have different names, they're basically going to be constitutional isomers. If they have the same number of atoms and they have the same names, then they're going to be identical. So watch how I quickly go through this. The first molecule would have this as its longest chain, leaving us with this particular numbering and a methyl substituent on carbon 4 and carbon 2. If you investigated the right-hand molecule here, you'll notice that he also has a 6 carbon long chain. Numbering him the correct way would be in this particular direction, right to left, putting substituents methyl right here on carbon 2 and on carbon 4. So, naming these molecules, we get the same exact name. They both happen to be 2,4-dimethylhexane, which means these structures are actually identical. Notice again how nomenclature helps verify that, so that we don't have to eyeball this on the exam. Let me show you another example to make sure you got this. It says again, are these following compounds identical or constitutional isomers? And again, we notice that to the naked eye, they don't definitely look exactly the same. So let's try to name them. The longest chain for the molecule on the left would be this, 6 carbons long, and contain 2 substituents, one here and one here, both being methyls. Whereas doing the same analysis for the molecule on the right, we end up with this right here as the longest chain, and numbering him correctly, we would end up having a total of 7 carbons in the longest chain, and only 1 substituent. Now, step back and notice both of these molecules do have the same number of carbons, and they have the same number of hydrogens. However, though, the molecule on the left is 2,4-dimethylhexane, and the molecule on the right would be 3-methylheptane. So, these molecules technically have same number of atoms, but different connections, and that's why they are called constitutional isomers. Now, let's look at one more nomenclature problem to make sure we got this. Watch what happens here. If we want to name this molecule again, we'll start with step 1 here and find the longest chain. And notice right here in this box, you'll find a longest chain. If you count all the carbons in this box, you're going to end up with 10 total carbons. However, watch what happens here. This is also considered a longest chain as well. Notice if you count the carbons in this box, you're also going to get 10 carbons. But this problem is different from the one we did earlier. In this case, we're not going to end up with the same substituents in the 2 different numbering ways. For instance, let me show you what I mean by that. Remember, if we pick this as our longest chain, then this would be a substituent here. We'd have this substituent, we'd have this as a substituent, and one right here as well. But if we consider this the longest chain in the molecule right here, then we have this substituent right here and this substituent over here. We get a total of 2 substituents. So what do we do in this case? Well, it's very simple. If this happens to you, then all you do is pick the longest chain that has the more substituents. Notice numbering it using the first way, we end up with 4 substituents, and 4 substituents are more than 2, so this now defines the longest chain. Now remember, why is that so? That's just the way nomenclature works in organic chemistry. So now that we know what to do here, let's just finish it off here. With 10 carbons being our longest chain here, the parent name of this molecule would be decane. We're now ready for step 2 here. Let's number the carbons correctly. In this case, we'd want to number from left to right to get the low substituent numbers. That brings us to step 3, circle and label here. We've already circled, so we'll label now. This is a methyl substituent, so is this one down here. We got a butyl substituent here, and we got an ethyl substituent right here. We're now ready for the last step here. Let's put all of this into the name alphabetically. What we would do is we would start with B for butyl, 5-butyl, -6-ethyl, -2,4 dimethylhexane. So again, when you're trying to name a molecule and the 2 potential longest chains of the molecule give different sets of substituents, always choose the longest chain that has the greater number of substituents. Now, at this point, you should go to your textbook and practice as many nomenclature problems as possible. This is something that you just can't have somebody show you how to do. You need to think through the problems yourself in order to master it.